Okay. So first I want to talk about the answer key from point 4 involving these wage data from the American Community Survey, which is extraordinarily large and ostensibly nationally representative effort conducted every year by the Census Department, which doesn't actually just like do one thing every 10 years. It does stuff all the time to kind of fill in the gaps with the decennial census and whatnot. So it has data on wages and on other things. And so for this, I used Connecticut. You could have used it in any state that you want. But like many data, particularly these days, the income variable is top coded. They do that with income and age and some variables like that, so that no one or people have less opportunity to individually identify who these people in the data are. If, you know, Jeff Bezos or whatever got sampled and reported an income of like $500 million or something last year, people would be able to look at the data, see who that is, and then know stuff about. That is protected by federal privacy laws. And this has gotten even more salient in recent years because the techniques that have been developed to de-anonymize anonymized data have become increasingly sophisticated, and so the Census Department has to resort to stronger and stronger measures to preclude that from happening, including introducing recently what is known as differential privacy, where they change some of the data values to be wrong before releasing them to the public. And that has been controversial and perhaps unconstitutional for the purposes of deciding how many representatives each state should have. That's, I think, still pending before the Supreme Court, but for other purposes, may very well be permissible for the Census Bureau to do this, and they have been doing that among other things to try to continue to tackle this problem. So many studies have used these data from previous years, and you can get all years going back good ways, to model income. And it doesn't have that many great predictors. People try to merge other stuff in. But among the ones that you might think of, years of schooling, male or female, age, maybe some other things. But those would certainly be among the core predictor variables that would be used in almost any microeconomic model. And those models almost always model the logarithm of wages as a function of predictors like years of schooling, which is essentially to be estimating a multiplicative model for wages. But if you model log wages, then the product becomes a sum. And we have this expression here for the model matrix, which we can then subtract the means from to get center variables. So this top coding phenomenon, which is fairly common, census data, other similar sorts of data might get from other sources, has the same structure almost entirely as the survival models that we talked about last week in the realm of public health, epidemiology, and stuff like that, where in this case, the actual underlying data is observed by the census. So if you are an employee of the census and you have like security clearance and stuff like that, you can see the actual data. So it's a little bit different. but the data that is released to mere mortals has this top coding phenomenon. And that mirrors the structure of what we saw last week in these public health studies, where the study ends, but the person isn't dead yet. So the outcome variable that's recorded is just they were still alive and kicking at the end of the study. And so no one really knows, or at least no one of the researchers really knows how long the person lived beyond the end date of the study. You get these outcome variables where you observe either exactly or a lower bound. So in terms of the generative model notation, the outcome that we observed is y star. If y star is less than the threshold for top coding, which I believe in Connecticut was some 770,000 stuff, and like a little over 1% of the observations were top coded, which is say the true wages greater than C, and so it gets reported as C. One thing is a little different from last time. Here we're using normal errors, but on log wages. And so in order to get back to wages, we have to anti-log eta plus epsilon, where epsilon is drawn from the normal distribution with standard deviation sigma, and sigma, where our beliefs about sigma are exponential with the rate of r. As usual, eta has the usual construction with intercept relative to centered predictors, and so it can be interpreted as the expected log income for someone whose all their predictors are average. And we can put normal prior on that, as well as the coefficients on the predictors. Questions so far? Then to draw outcomes, you might think, well, what do I think average log wages is? Kind of shouldn't matter too much because the logarithm function is so extreme that it should turn this into some number between 10 and 15. And so we need to choose our priors on the, not just the intercept, but also the coefficients and the standard deviation and the errors to, you know, keep the model in the sort of 10 to 15 range for log dollars. And to do that, we've got to have priors that are pretty close to 0, fairly well concentrated around 0, especially in this case, where I include not only age but age squared. The theory there being, you know, young people tend to get paid less, but then you get paid more when you're older. But then when you get really old, well, one, you might retire, but even before you retire, you might be working less. You might not have really modern skills. So, you know, your wages could be low. As part of that, I did what it is I usually do, which is to measure age in decades rather than years, because for most purposes, this one including a 1-year difference between people basically is too small to really even think about what the difference might be. Whereas 1 decade difference between people, it's kind of the smallest unit of age that we can really think about mattering. But anyway, so we just observe C from the data, we draw gamma, draw each of our 4 betas, draw sigma, as if this was going to be a regular linear model. And then we row-wise on our 1,000 draws or whatever, gamma plus beta 1 to x1 all the way to beta 4 times x4, draw an epsilon, 1 for each observation from normal distribution with standard deviation sigma. We get anti-log the sum of eta and epsilon to get y star, and then the y we observe is y star if that's less than c, otherwise we observe c. Yes?
What rate did you set? I missed it.
I did 1 here. Ambitious, but you know, if we think log wages is between 10 and 15, for the most part. Could we get it within one on average, knowing years of schooling, sex, and age? Yeah, maybe. Other questions? Again, we've done quite a number of these things so far, and we'll continue to do a few more. The bottom part is usually not changing very much. All I'm doing, for the most part, is tweaks to how the top part works in order to have a model that is appropriate, or at least more appropriate, for the way in which the outcome variable was measured. Continuous, count, binary, censored, ordinal, which we'll talk about today, later. But anyway, so do the same, draw from the prior predictive distribution, always important. Had to do this a few times to get something that looked as reasonable as this does. With the anti-log transformation and stuff, had a tendency to go too far to the right, get too spread out, top code too large a percentage. But, once you see it, then you can say, okay, what do I need to do to rein this in? So we got this. Still right skewed, but it, seems now a reasonable median. More than adequate, considering how many, tens of thousands of people are in the data set for each state, no matter what state. So this is certainly not a normal looking distribution. First of all, it's not even the distribution we're modeling, because this is wages in dollars. We're actually modeling log wages. But even then, if you look at the code, by construction, the errors are drawn from a normal distribution. And that's the assumption of a model. Given the predictors, the distribution is normal. So net of the predictors, multiplied by the respective parameters, you get the errors. And that's the assumption being invoked here. But that's also, even then, that's not exactly it, because what's being claimed in the generative model, or what's being assumed in the generative model, is that the errors are normal with mean zero and standard deviation sigma. If we marginalize over sigma as well as everything else, the errors are going to have heavier tails. When you anti-log the thing, it's going to get more override skewed to it. So the generative model implies the outcome that we see here is very much not normal, even though it clearly assumed the errors to be conditional on sigma. And then we have exponential bias. Questions? All right, so once you figure out a generative model, have a reasonable set of draws from the prior predictive distribution, you're ready to go, or almost ready to go once you put in your priors. Same as what I had before. I can call BRM with that same formula. Data family is Gaussian, prior what I said. And if you look at the output, certainly should get a negative coefficient for the sex variable. If we evaluate rather than test the research hypothesis rather than the null hypothesis, that women are paid less than otherwise equivalent unobservable men, we get a posterior mean estimate of negative 0.39, and it's estimated very precisely 90% of the draws are between negative 0.42 and negative 0.37. None of the draws are positive, therefore our best estimate of the posterior probability that this coefficient on sex is negative is we're certain. You go to C, And so if we had multiple models, we could compare them with respect to the expected logarithmic density, or we could average them by choosing the weights that maximize the expected logarithmic density of the average. Here, if you do the model that I did, actually get all the proto-K estimates to be very small. So we're good here. This, as usual, cannot be interpreted in absolute terms. But the difference between this and the model speaks to the difference between how well this model is expected to predict an equivalent number of future observations relative to some other model. So we can do model comparison that way. We can also use the Pareto smooth importance sampling weights, or more specifically their CDF, to in conjunction with prior predictive checks, whether that's this overlay or Lu intervals, anything with Lu in it. And in this, oh, we have a question over here.
Yeah, so I did something very similar to model very similar with keywords, and I also got this sort of like S-shaped pattern on the peg overlay. And then when I ran it using the other function that we used in class, it was like the PP check function. It looked really periodic. It was like a similar shape to this, but it was like bouncing up and down a lot. So I was wondering, is that just like the kernel, the kernel used by these two different functions is different, and it's I don't know.
Possibly. I think that may be saving the forest for the trees here a little bit, and that this model is not calibrated particularly well. I think you'd probably reach that conclusion irrespective of what model that you estimated. That's why, actual economists have to figure out how to merge more variables into the census data, or something like use this as kind of a baseline or whatever, because the variables that the census collects are, really not super adequate for the task that we did on homework. But an important part of the task that we did on homework was to get to the point where you can see that this model is not so good. However, one of the reasons why this model does not look so great is because we actually looked. And we have a posterior distribution to average over. We can analyze the calibration properties of the predictive distributions, none of which we could do if we just had frequentist point estimates, of which there are probably hundreds of thousands in the literature for like what determines wages. And they have their frequentist measure to fit. They test a null hypothesis that one model fits better than the more general model, or not as bad, whatever they do. But they never get to the point where they could even make a plot like this and be able to say, this is not well calibrated. It's sort of over. The weights are too high, kind of in the middle and to the right, and not so much. So it could easily look worse, unless you don't look at all. As we said before, but it bears repeating. These leave one out cross-validation concepts used in plots like these pertain to the way in which we're estimating the expected logarithmic density for in future observations under our model, but irrespective of the predictors. Given our priors, given the normal error assumption, all that, yes. But irrespective of the parameters, beta, gamma, sigma, whatever else it may be, we're averaging the fit method over all that, weighting by the posterior distribution, posterior density. And that is a much more appropriate, but yet different, than what frequentist and supervised learning do which is to evaluate the fit of the model conditional on the optimal values of the parameters. In the case of maximum likelihood, the parameters such that the most likely data set of size n to observe is the data set that was observed. By construction, any other data set of size n that's randomly sampled from this population, you'd anticipate that it's going to fit worse to these parameters than the data set that yielded the parameter estimates by optimization. And it's the same with supervised learning, even though they're penalizing in order to shift the supremum over. They don't have a posterior distribution to average over because they're extraordinarily reluctant to introduce probability in the idea of estimation. Because they really, really, really want to only use numerical optimization to obtain point estimates, to obtain a vector of numbers, rather than a probability distribution over the parameters conditional on the data. And so, we'll get into that maybe a little bit more, but that's the kind of fundamental difference between the way Bayesians predict and the way not Bayesians predict. And that allows us to do things like predict wages, or log wages, and then we can anti-log that, and then we can average over the people to get an estimate of log wages, or wages in Connecticut that is not adversely affected by the top coding process that inevitably happens with actual census data. And in this case, I get a plot. Looks something like this. Red line, average of the Y values that were observed for Connecticut. Black line, posterior density of the average wage. Latter is clearly a lot bigger. Good. Well, one, we're pretty somewhat uncertain about it. But also, it's at least 10,000 higher due to the selection mechanism induced by top coding. So the average wage includes the Jeff Bezoses of the world and a whole lot of other rich people who live or work in Connecticut. And so if you pretty much exclude them or only include their first $700,000 of income, you get a badly, downwardly distorted estimate of any expectation, including wages, but also variance, anything having to do with income inequality. If you're like estimating the state tax revenue that they would get in Connecticut, off the top coded data, your budgets would be like completely wrong, etc. So this makes a big difference. This makes a difference in a fairly obvious way. It underscores how sensitive things can get when doing anti-log transformation, particularly if you already start with something that is like pretty variable and right skewed. But it makes a big difference. It makes a difference in an obvious way. So like the red line is fairly obviously wrong, even though the black line comes from a model that had some issues with it. It's trying to do the right thing. But if you look at the empirical literature, you're going to see over and over and over again, people just take the numbers that are in the data. It's like 1%, whatever. 1% makes a huge difference. So it makes a big difference. It's a fairly obvious mistake, but it's a mistake that happens all the time. And social science has just decided to kind of live with it. Because, what are you going to do about it? Like the way to actually deal with this problem would be to break into the census office and get access to the underlying data. That's the only way that you could really solve this problem, except for modeling that problem with a generative model for the data as observed, which includes, well, as observed by you, which is after it's observed by the census guys, and they top code a little over 1%. Questions? Okay, question.
What do you do by the diagnostics? So, like for example, for paper, I might get that, but for the PSI diagnostics, it'll be like below 0.3. So,
Yeah, so in order for the Pareto-smooth importance sampling, leave one out, cross-validation estimator of the expected log predicted density to be a valid estimator, all the Pareto K values need to be below 1, and if any are above 0.7, then the properties of the estimator are not really good for smaller samples, right? Anything that's less than finite. So if they're above 0.7, if you get the warnings, fairly easy fix. ReLU equal true, re-estimate the model a few times, each one dropping out the problematic point, and then like leave one out for real, and then that goes into the estimator along with all the things that are estimated by PSIS LUCV, or moment match equal true, does another correction to eliminate the or reduce the bias from those people. So if you get the warnings, do something about it, but it's not that hard. To then get a valid estimator of the expected log predicted density that doesn't really take too long to obtain. Much less than what it would if you did literal leave one out cross-validation with 10,000, 20,000, 100,000, whatever it is, observations. You'd have to re-estimate the model n times. Which is why literal leave one out cross-validation is not that popular in supervised learning, even though supervised learning is all about cross-validation. They tend to do stuff like k-fold, where k is 10, and you put like 90% of the observations in and 10% out or something like this. That costs you, from a Bayesian perspective, that costs you posterior precision. So we want to reduce that loss as much as possible by just estimating what would happen if you left one person out. That's negligible. Leaving out 10% is noticeable. Okay, so the second question was on this article by Leo Brayman, which is sort of seen as foundational to a lot of modern stuff in supervised learning, data science, statistics departments. It's even become more prevalent in social sciences. So what all did you think about that article? How did you, respond to some of the things that it prompted you to respond to in that article and articles by other statisticians that were responding to that? So what did you come up with?
One of the things that stood out to me is just that one big point of using statistics, particularly in economics, is designing interventions that you think are going to have causal effects, and you want to try to identify causal effects. I didn't think he had a great response for why an algorithmic modeling approach can get you causal estimates. He said you can identify important input variables, but important is the same as causal. And whereas people in the data modeling, using that in the data modeling culture, are doing a lot of work to try to figure out what are ways
Yeah, so I think that's a fair characterization of what was said 20 years ago. It's also fair that people from supervised learning are thinking about that more now than they used to. They're trying to do some stuff, but they're trying to do some stuff in a framework that is deliberately limited, and constrictive, as compared to the culture he was criticizing. Cool. What else we got?
I think the Cox reply kind of spoke to one of the big issues that I had in that the data modeling camp was kind of portrayed as like trying to just make up things that fill the box with a data model, whereas like the consulting experience pieces where they're like, just throw everything in this black box and find out what's important. They kind of their values, the more was it subject matter expertise portion of the Venn diagram at the bottom. So I don't know, it seems like from a more Bayesian analysis, like how does that fit in? To me, that's still more than the data modeling camp, because you still need to create some type of, or have some type of background understanding of the relationship between the predictors and an output variable in order to create bias that makes sense. So I don't know, it seemed like from that point it was more of a geared towards prediction, just throwing everything in this black box, and that works better, and not so much like subject matter expertise or
And certainly reflecting of a value judgment, which was rare at the time, 20 years ago, but has become probably the majority today. The way in which models should be evaluated is how well they predict in the testing data. And that's it. Definitely a value judgment. Fisher might even call that subjective. Maybe. So, what more in terms of whether you think Bayesian is like a third culture? Is it like a subset of one of the cultures? Is it like straddling between the two? Where does Bayesian fit into Raymond's view of the world and or the people who were responding to him?
I feel like what we've been doing so far, a lot of it's been data modeling, and now we have to specify bias and we have to specify model. And I think it comes up with what I said, it's really a big cultural philosophical difference where one focuses on predictive power, and then that's it. It doesn't matter if it's a black box or the other. The classroom goes out, and it's basically you can do either depending on how you sort of specify a model and how you what you want to get out of it. So in terms of goals, I think it's a bit ambiguous, but in terms of design, it seems to fall in one under the model we have.
Yes. So Raymond would certainly think Bayesian is part of data modeling, and even in 2000, there wasn't that much prevalence of Bayesian, so you can understand in sort of a manifesto style article, you wouldn't get into that sort of level of distinction among data modeling, among statisticians. Well, I think what he said is right in that the Bayesian framework, because it's an overarching framework, it's coherent, etc., permits you to do, either the causal inference sort of stuff, or the predictive stuff, or, finding missing airplanes, whatever. It all fits in the same framework because the Bayesian is a system of managing the beliefs about what you think. And so it doesn't put any restriction on what it is that you want to think about. So that could be predicted in the future. Would you have something you wanted to add on that?
Yeah, so I really had a lot of similar things to say about the Bayesian culture. I thought and I thought it fit pretty well between them. But again, from the perspective of philosophical differences, right? Putting your prior beliefs in, I thought that was really what differentiated it and possibly made it kind of its own culture, is coming in with that framework. But again, these priors and beliefs, whether your black box is filled with these equations, these models that you think work, or is empty, you can use these kind of beliefs to fill that black box like you were saying with.
Yeah, you kind of, in addition to like, you can, I think, more so today than 20 years ago, you can kind of choose as to like how much you want to put into the box explicitly versus how much we want to just get it from the data. You can't just do something purely from the data. You have to put like some kind of structure, and even the things that Raymond are talking about with these supervised learning and stuff that's become popular, neural nets and random forests and stuff like that. They're still putting some structure, like these functions are continuous. That seems like kind of reasonable. Like it's hard from a data modeling perspective to think of any like data generating model where we would have like jump discontinuities in a model for like wages or something like that. But restricting it to continuous functions is a structure. And there are very few continuous functions compared to how many discontinuous functions there are, like, that we could imagine, or even that we can't imagine. And then, most things in statisticians will go even farther and say the relation to the function is differentiable. That's an important part for Stan. I haven't really dwelled on it because, like, it's kind of innocuous, but it's using derivatives in order to get around the posterior distribution. So your posterior distribution has to be differentiable with respect to the parameters at almost all points in the parameter space. That's a structural assumption. Seems innocuous, but the number of differentiable functions is tiny relative to the number of continuous functions. And the number of continuous functions is tiny relative to all functions, continuous and discontinuous. And so all of this involves putting structure on, but particularly with the Bayesian perspective, you can kind of choose how much or how little, and you can use that to do whatever it is you want. Among those things, as was mentioned, you could do prediction stuff, and you can evaluate that with expected log predicted density. And so it seems like from that perspective, well, you could kind of accomplish the goals of what Riemann wants to accomplish with algorithmic, or at least the evaluation of models based on how well they predict outside the data that they were used. What Riemann would call trained on, Bayesian would call conditioned on. But like, what do you think the role of like evaluating stuff with ELPD fits into this discussion? Debate, food fight.
Probably both the model selection piece as well as the predictive accuracy piece. So there's the whole section talking about flaws in model selection using like Bayesian or whatever else, and the inherent issues that come with that. And there's also a whole section on predictive accuracy and using approximation. Talking about the ELPD fits into that, but where it gives you the ability to take kind of the hypothesize posterior distribution of an unobserved new data set as opposed to like cutting your data.
You can do all that. And I think the ELBD accomplishes supervised learning's reported goals better because one, it's irrespective of the parameters rather than at the optimal parameters, albeit obtained from the testing data. It also is for the actual expectation of future data. With supervised learning, it randomly usually carves out 20% of the original data to put in the testing data. But that's past data. been collected. So any random or otherwise idiosyncrasies in how the testing and the training data got split from each other are going to be reflected in the point estimates of the optimal, and thus the predictions, and thus the fit metric, and thus the conclusion as to what is. Now, if you have truly huge data and you're randomly subsampling, it's probably not that big of a deal. But these sorts of things are applied in social sciences, which by any standard that's used in like the tech industry are small data. Even if in this case we're taking data from the Census Bureau, that's thousands, maybe 100,000. Maybe if you put all the states together, then it would be like over 1 million or whatever. But we're not talking billions. So these things are certainly used when the data sets are finite. And thus, you can randomly get a weird testing set. Like, if you had randomized in another way, you would have got a different training testing split and possibly a different conclusion. And so the fact that all this supervised learning stuff, the predictions are not only at the optimal parameters, ignoring any parameter uncertainty, not as opposed to the Bayesian thing, which is marginalized over the parameters. Consider the fit metric averaged over the parameters, weighted by the posterior. And the fact that the ELPD pertains to the actual future that hasn't happened yet, as opposed to this proxy of the future from the past that is the testing set. And as a result, it tends to yield well-calibrated predictions. Indeed, it can be proven Bayesians produce the best calibrated predictions if the model is right. And that's where I think Riemann and a lot of supervised learning people would take issue is, well, those guarantees are only if the model is right. What if the model is not right? And there's certainly plenty of reason to suspect that is the case. And so if you're going to argue for supervised learning being preferable to Bayesian, not just on like how much computation time, but on kind of like theoretical grounds or whatever, you pretty much have to start with, well, the models are wrong. So what sort of fit metric or ways of accounting for that should be done, since the models are inevitably wrong. And like that's true enough, but it doesn't necessarily follow that we should give up on trying to make good or better models and throw away all the stuff that we get from probability. So on that note, Drew Conway or whatever has this Venn diagram, and you'll see many other Venn diagrams like that that characterize data science as the intersection of a whole bunch of things, at least 3 in this case. And certainly a lot of the things that Raymond was arguing in favor of have become more prominent these days, especially among people who self-identify themselves as data scientists. But if you just sort of looked at this and didn't, read the article or know where it was from, and you just said, okay, well, you got to have like substantive expertise, you got to have knowledge of math and statistics, and you got to have hacking skills, which is sort of a pejorative way of saying like the ability to, use algorithms and stuff. Conway would also include the ability to like scrape data just to get it in before you even model it. But if you just looked at this, maybe without the specific words, just looked at substantive expertise, math and statistics knowledge, and like algorithmic capacity, you would say the intersection of that is Bayesian. You gotta know probability theory. You gotta know enough about the substance of your problem, not only to specify priors on the parameters, but also the rest of a generative model, including what predictors to put in, the interactions, like all that. And then you got to be able to use MCMC to draw from the posterior distribution of the you specify, using your knowledge of probability in addition to your substantive knowledge. And yet, so this middle section here says data science rather than Bayesian. Even though, you know, the Bayesian stuff, like all three aspects of it, started to become feasible in 1990 at the latest, with the invention of the MCMC algorithm. And so data science programs and whatnot didn't start popping up until about 2010, let's say. So the Bayesian thing had been feasible for good 20 years before data science programs started to become a thing, even though data science ideas have been bouncing around for a long time before that. But, you know, as data science was sort of getting established as its own field, Bayesians had been doing and had a framework for doing what they thought to be data science, except we just called it science. And so a lot of Bayesians are understandably a little bit perplexed as to why data science programs, data science concentrators, millions of people on LinkedIn who identify themselves as a data scientist are not using Bayesian techniques. And what you tend to see data science do these days, I would say, is more in the northern part of data science, the way Conway drew it up, maybe even somewhere over here. But the whole thing is kind of squished this northeast. And so less emphasis on substantive expertise, less math and statistics knowledge, at least for probability, definitely. And more, oh, I know an algorithm, or oh, I can code something and run 100 different models at once in parallel and like get results back in 2 seconds type deal. So that in my view, this symmetric depiction, which I think Conway was sort of idealizing, but that's what he hoped data science would be, is this kind of symmetric thing. It's become quite asymmetric, maybe not even overlapping very much, and then it's a lot up here. And yeah, so to take a extreme but common example of that, Data Science Day. I'd say every day is Data Science Day these days, but Data Science Day is happening at Columbia next Wednesday. I think it's free for students. Where the Data Science Institute is going to be having all kinds of speakers, posters, presentations, some of them from data science students in that program, but also from people in industry like this person from JP Morgan Chase. Lee Bollinger is going to be there. So, you know, it's got to be pretty important if Lee is going to show up. Jeanette Wayne, who used to run the data science program. Kathleen McCann, who's the founding director, etc. But if you look through all these like lightning talks and keynote talks and like presentations that are happening or whatever, how many of them involve Bayesian? Just a guess. Ballpark figure.
0.
Not a damn thing. So, from a Bayesian perspective, you might very well ask yourself, well, if we're not doing this, or we're just maybe doing a small part of this, like right up here, Where's the science in data science? What do data science contribute to science? And why are they doing it in a non-Bayesian way? Even though they knew 20 years before they really got started that the Bayesian thing had become feasible. And Fisher's arguments as to why Bayesian was inappropriate for science were no longer taken seriously by anyone living. Questions? All right, so let me sign into this again. Talk about ordinal models. Using BRMS. So while it's going, might as well get this out of the way. Columbia policy, etc. But again, this week, like last week, it's 99% Paul Berkner, and the remaining 1% does not include me. It's just BRMS uses stand to obtain posterior draws from the model that you specify in the R language using BRM. And so that implicates me among a lot of other people, but other people don't have the conflict. So if we go back to these data, which you should load up from week 9, on the poll conducted the day before the election in 2012 between Obama and Romney, I've coerced the urban density to be ordinal, which is arguably appropriate in political context, order from rural to suburban to urban, particularly because this particular data set did not ask about the person's race, which was perhaps relevant to a presidential election between two people of different races. We can group the data in order to use a binomial likelihood. And the age and income are also ordered factors because they were measured as buckets on like a Google form, rather than you write in your exact age. And in many situations, you might want to assume that the effect of some ordinal variable on eta and hence on mu is monotonic, which is to say if we observe the person's exact income or exact age, we might well have put that in as linear. Wouldn't have to be linear. We could do polynomial. But we might very well put that in as linear. And so linear is obviously monotonic. And so if we have these measurements of the underlying concept that are discretized but ordinal, but they often reflect some underlying continuous concept, that if we were to model, we might use a linear specification, then there's a strong justification for using some sort of an ordinal construct on the dummy variables that come from these ordered variables. And this is something that makes social science a little bit different from a lot of the other sciences. We have, it depends on the subfield, but have probably more ordered variables than we have variables of any other type individually. So yeah, I mean, it's probably like 30% ordinal variables or something like that in the social sciences. Whereas that's not really a thing in, physics. And less of a thing in economics, but, certainly for other social sciences, these sort of ordinal measurements of underlying continuous concepts happen a lot. And to deal with those, we need a distribution over the parameter space of probability mass functions. So that's kind of like a little bit disconcerting. But there are distributions, the most simple of which is known as Dirichlet. So that has hyperparameters pi, which are non-negative, it's sum to 1. It has over the random variable pi that's non-negative, it subs to 1. And it has a PDF, a probability density function for those given the shape parameters alpha that takes that form there. Two important things to know about the Dirichlet distribution. The expectation of the ith element of pi is equal to alpha I divided by the sum of the alphas. So in other words, the expectation is in proportion to the various alphas, and also if they're all greater than 1, then the most likely value of pi, alpha minus 1 divided by negative 1 plus the sum. Also, if you look at this form of the PDF, it's clear that if all the alphas are 1, then you just have pi raised to the power of 0. So that's just going to be 1, in which case your density is proportional to 1, which is to say all simplexes, random vectors that are non-negative and add up to 1 of size k, are equally probable, which is not a bad prior in a lot of situations, although you might be able to do something better based on your substantive knowledge. Dirichlet includes as a special case the beta distribution when k is 2. So in other words, Dirichlet is a generalization of beta to a situation in which more than 2 things are possible. And notice that pi is non-negative. It sums to 1. So if we take, oh, you can't see that. That's better. If we take theta sub k to be the cumulative sum, the running sum of the pi's, then theta k is the sum of the pi's up to and including the kth element. And that construction is used in the models in the paper by Paul Bergner and his co-author, Sharpit there. Now, you don't, just because a predictor is ordinal doesn't mean you have to use this product. You have the option to use this product if you believe that the coefficients on those dummy variables should be either increasing or decreasing, which in a lot of situations that sounds reasonable. So for the data set we're considering, or the Obama-Romney business, we could say that has binomial trials being the number of people who fall in that demographic stratum. And you have some CDF, either normal, logistic, whatever, being applied to the ETAs to give you the probability of any one person in that group voting for Obama. Eta is the usual form with an intercept plus coefficients times mean deviated variables. We have a prior on the intercept. But what's different this time is rather than saying beta is like drawn from some normal distribution, whatever, we're defining beta to be lambda divided by k times the cumulative sum of the pi's. Okay, so what's the distribution of the pi's? Dirichlet with shape vector A. And we have a normal prior on lambda, let's say. So what's going on here? So by this sum is going to be some number between 0 and 1, the cumulative sum of the pi's here. And then we're scaling it up by lambda, which is sort of like the overall magnitude control. And then we're dividing by k so that it can use the same construct no matter how many categories we have. And so lambda is kind of like the average increment in beta compared to the previous beta, if you work it out that way. And if you really think this is monotonic, then your prior lambda should probably not be centered on 0. It's a little weird to say, yes, I'm sure this is monotonic, but I don't know if it's positive or negative. It could be 50-50 either way. But in a lot of situations, I think you have a pretty credible claim as to how the prior distribution, where most, if not all, of the prior probability density would be on one side of 0. Now you can have a little bit that's looping over just because there's some chance that something that you think is positive is actually negatively related, but whatever. So In order to do the draws, we draw gamma from its distribution, we draw lambda from its distribution. There's no function in R, unfortunately, to just draw from a Greeklet. There is in Stan, but the way it can be done is by drawing from a bunch of gamma distributions that have shape A, and then dividing these chi's, which are realizations of independent gamma, divide them by their sum. And so then pi is going to sum to 1 over all k elements of pi. And if we take the running sum, the cumulative sum of pi, we get what was called theta on the previous slide. So this is theta k, and then we multiply little k, and we multiply by lambda, divide by big K to get our construction for beta, which is equivalent to what. So this cumulative sum of a positive, they were in this case simplex, puts the betas in order. And that can either be increasing order if lambda is positive, or decreasing order if lambda is realized to be negative. And so we can use that to get a more nuanced prior that may reflect the information that we think at the time, before seeing the data. Questions on that? So how would we draw from the prior predictive distribution? Well, first we'd set up our X matrix as before, go row-wise on the parameter draws, construct eta as usual, construct mu as, let's say, standard logistics CDF applied to eta, so eta is log odds, mu is the conditional probability, and then we make a copy of urban density because I'm going to need it in the plot on the next slide. And then we draw the outcomes from a binomial distribution, size equal to the number of observations in that strata of the pole, and mu the conditional probability for the people in that strata, which under a binomial distribution has to be the same, but that is going to be the same when we don't have any variables that actually vary by individuals. We just have a whole bunch of groups carved out from the intersections of these demographic variables, and this is not rare for poles or other stuff in this sort of science. So then we can plot this a variety of ways, inclusive of this. Here on the vertical axis we have the probability of favoring Obama. On the horizontal axis we have the 3 ordered categories of urban density: rural, suburban, and urban. And our model reflects the assumption that the relationship between the probability of voting for Obama and this urban density thing is monotonic. And because the prior I put on lambda was 1.575 normal, in this case we've assumed in all probability that the relationship is increasing, which is to say people in urban areas more likely to favor Obama than people in rural areas. It's just a question of the magnitude, getting something reasonable there. And that magnitude is controlled a lot by your prior on lambda. And so you might say, well, okay, this is an increasing relationship in the medians, and that kind of makes sense. But you might think the relationship is even more extreme than what you see here under our prior. That in 2012, it's not like rural people had a 45% chance of voting for Obama over Romney. It's probably even less. It's not as if people in urban areas had a 55% chance of voting for Obama over Romney. It's probably even more. So you could certainly defend an even stronger prior, or more concentrated, or shifted over more prior lambda to put more slope into this monotonic relationship. But this is getting at something reasonable and might appeal to someone who is skeptical or professing skepticism about the salience of the urban, suburban, rural trichotomy as it's applied in elections. And something similar with income and age. So if we look at the default priors, and you should only look at the default priors to know what they are, not that you should use them. In particular, you should not be using improper priors on the coefficients. They have a Dirichlet with a shape of 1, which is fine. For the pi's, they get transformed into the thetas and they get transformed into the betas. So assuming uniform over the simplex for that is probably okay. Prior on the intercept, way too heavy tails. And then in here, okay, there's a coefficient on gender for males, and there's coefficients on 3 out of the 4 regions. Those are not ordered. I mean, anything with 2 categories you can say is ordered, but you don't need an ordinal prior in order to make that happen, because it's just like 1 and 0. Happens automatically. These Mo age, Mo income, Mo urban density things, those are the lambdas that get multiplied by your cumulative average, or cumulative sum divided by k. Business for the variables that you specify to have ordinal relationship. So those are things that you should ordinarily have pretty strong prior beliefs about if you are using ordinal construction in the first place, or monotonic. If you don't want to assume monotonicity, then just make it into a variable, just put separate coefficients on it, and it won't reflect that. So those are the priors that come out of what I just said. Then you can use the BRM function with binomial link equal logit to estimate the model. And then if you look at the parameters that pertain to this lambda business on the next slide, you see we have a pretty negative 1 for age, reasonably positive 1, a little bit more uncertain for urban density. Income is more likely to be negatively related to the log odds of favoring Obama, but it's not estimated very precisely at all. And there's probably, 15–20% chance that it is positive under our posterior distribution. These are the Dirichlet things, so they sum up to 1 within the thing. These are also not so precisely estimated, but they're very negatively correlated with each other, because by construction we're talking about things that sum up to 1, and so you can get reasonably precise posterior distributions about the coefficients beta, even despite this, if the data suggests that. And so we want to visualize the same thing, or same concept that we had before, but now with the posterior draws, rather than the prior draws. We can call posterior lit red to get a 4000 by n matrix of the posterior distribution of the log odds. Apply the inverse link function to the log odds to get the expectation or the probability of any 1% within of those demographic groups favoring Obama, and then we can use ggplot to visualize those probabilities against the observed values of the urban density factor, and we see, indeed, there is a positive relationship. And it also seems like this one doesn't have that much of a slope, and the scale is different. But anyway, this is what it came out estimated to be with the posterior distribution. But certainly, if you had a more extreme prior distribution on the lambda for you would have gotten a somewhat more extreme looking posterior distribution on those things. Questions about that? Again, these models, because like everything's in terms of eta, you're not really accepting a very linear model with no link function, no interactions, like nothing at all going on, just plain linear. That's the only situation in which you can look at a coefficient and that be sort of sufficient for interpreting the nature of the relationship between that predictor and that expectation of the outcome. Every other situation, definitely including this one. No parameter can be interpreted in isolation from any of the other parameters. No predictor can be interpreted in isolation of that. But we can call posterior limb pred, e-pred, predict, whatever it is we need to get stuff in log odds, in probability, in counts. And so then we can plot those relative to whatever we need to making visualizations in appropriate units. And the parameters, by and large, are not.
So the posterior limb pred is in terms of data, right? And p-locus is what converting that into probability.
Yep. So subtly different from posterior e-pred in this case because our outcome is binomial rather than Bernoulli. So if I call posterior e-pred, it would be the expectation of the count. So probability multiplied by the number of people in that strata. Here I want view the probability of an individual within each demographic group. Voting for Obama to look this up. Now, BRMS puts considerable effort into making it easy for you to make plots like this with the so-called conditional effects function and a plot method for that. So if I wanted to make a plot like this, to show the relationship between the probability of voting for Obama and the age of the person, which was also assumed to be monotonic in the priors. And I put a negative coefficient on this lambda. And the posterior distribution is consistent with that. Older people, very low probability of voting for Obama. Young people, very high probability of voting for Obama. Relationship among those, not linear, but strictly decreasing. And that was the assumption of this monotonic prior business. Which also allows you to sort of model or account for non-linearity relative to the underlying continuous concept. Yes?
Does it ever make sense to treat predictors that you have in absolute units as ordinal if you're not sure that there's a linear relationship between them and linear ranking?
Maybe. If there's not too many unique values, you could just say this is ordinal rather than ratio scale or interval scale. Could. We'll talk soon, not today. There's other ways that are probably better if you have a genuinely continuous thing to estimate a continuous but non-linear relationship that wouldn't involve the discretization that you were contemplating there. Posterior predictive check, not horrible. Certainly you were getting a few too many high. This is not calibrated great. I think this looks a little bit better than the one that we did previously, where we didn't assume monotonic relations. And so by doing so, we might have gotten a little bit closer to something good, even though certainly, people like Greenland say we should just give up on trying to do something good, even though these are based on predictive accuracy stuff with the leave one out cross validation concept. Okay, more questions about using ordinal predictor and the option, not requirement, option to use a monotonic relationship on the parameters. Okay. Let's think about another type of model, one with so-called interval censoring. So suppose the outcome variable is what is your income range. Now you'll find most of the surveys in social science, you don't just write down or type in like a number. for the most part, you check a box that has a bucket of, incomes that you could be. And so the outcome that we observe is some integer or label, more specifically, but let's just call it an integer label. 1 through capital J, if there are J income buckets that you could check when presented with the survey. And the assumption of this data generating process is that a person will check the box for the first category if their true underlying income Y star is less than C1, the first cut point. Where C1 is something that's observed by the person in the survey. It says like, is your income less than $30,000, between $30,000 and $50,000, between $50,000 and $100,000, between $50,000 and $200,000, or greater than $200,000, something like that. So the person doing the checking of the boxes is able to see the labels. And so these C's are considered known rather than unknown for now. And so if C1 says like $20,000, if your income is less than that, then our model presumes that you check the first box. If your income is greater than $20,000 but less than $50,000, or whatever C2 is, then you're presumed to choose the second box. And if your income is greater than whatever is the maximum category in the thing, then you're presumed to choose the box farthest to the right. Over 200,000. That'll usually be like whatever the last category is, something like that. Okay, cool. So what's Y star? Well, if we're talking about income, or at least if we're talking about wages, fairly well believed in the literature that log wages are normally distributed. Now, it's not an assumption you would necessarily want to make about income, and it's certainly not an assumption you would want to make about wealth. But log wages, that is a fairly reasonable assumption, in which case Y star would be the anti-log of eta plus the error. Cool. What's the error drawn from? Normal, mean zero, standard deviation, sigma. What are your beliefs about sigma? Exponential with a rate of r. Expectation of that is the reciprocal of r, whatever. Okay, how's eta constructed? Same way it's been constructed all semester. What's your priors on gamma and beta? So if we had data like this, where the census asks like what income bucket are you in, we'd really be estimating the same model that we estimated on the homework. But now everybody's income has been obscured by this observation mechanism rather than merely the top 1%. It's just the way in which it is measured. It puts you in intervals rather than any one specific number. But, up to Y star, it's the same as what we did on the homework. It's just a different assumption about the process of going from like actual wages to observed data about wages. In this case, we're talking buckets rather than what we had on homework, which for the most part was numbers with like one bucket for the top 1%. As such, the code to draw outcomes from the posterior predicted distribution is very similar to what we had on the homework, because it's the same up to Y star. We have this additional vector C, which again I assume to be known. Let's say it's 10,000, 30,000, 60,000, 100,000, 200,000, something like that, are the buckets that you can check yourself into. And so we draw gamma, we draw beta, we draw sigma from their respective prior distributions. Then we get row-wise to draw the data, presuming X to be centered. We construct eta the way we usually do. We draw epsilon from its normal distribution conditional on sigma, or the realizations of sigma. Like we always do, we make y star as the anti-log of that plus the error, and then we could use the cut function, which takes the underlying continuous thing and a vector of breakpoints to coerce that to an ordered factor 1 through 6, depending on which box you check. So that's our model for the generative process for how it is we came to observe someone with an income of 3. Again, we should not be interpreting 3 as a number, but rather than it is a label, but it is a label that has an order to it that everybody understands. So it certainly suggests as if we have sort of a type of ordinal outcome here, but what's different from what you saw in the reading, what we'll talk about for the rest of it today, C here is known, rather than some unknown thing that we have to estimate. But question? Yes?
So is y star like the predicted income in dollars, and then y, is that cut function just breaking whatever the predicted income is into C?
Relative to these cut points here, the survey ostensibly has. So yes, the prior predictive distribution of y star is in dollars, but y is in labels for everybody. Other questions? Yeah,
This is actually where it actually works.
going back.
Ordinal variables, we suburban one.
Predictors, yeah.
So what would be the difference between just using dummies for like each of the
Right. So in this case, probably not much, because even if you didn't assume there to be a monotonic relationship, you would have probably found a monotonic relationship in the posterior distribution. By using the prior in the reading, you guarantee that every realization from the posterior distribution is going to either be strictly increasing or decreasing order. So you probably would have found the monotonic relationship. It's a question, do you want to assume that from the outset in order to get more precise posterior distribution, not just of this variable, but also all the other variables, because particularly in a Bayesian thing, particularly in a GLN, everything is related to everything else. So the more certainty that you can put in through the prior, the more certainty you're going to get in the posterior distribution. And when your modeling assumptions are reasonable or defensible, that's something that you want to avail yourself of if you can get away with it. And I think in this case, probably not all situations with urban density, but with this outcome, Obama versus Romney, you'd be hard pressed to find anyone who, before the election, didn't think there was a monotonic relationship between rural and urban. Indeed, you would probably find that in almost every democratic country, irrespective of who's in the election, that the voting preferences of rural people differ depending on how rural they are, relative to the other extreme of people who live in cities. And that's because, urban density, if we measured it in like people per square kilometer or whatever, that's a continuous thing. We're just measuring it badly when we give people 3 things that they can check a box or it's actually click a button in this poll. So we really have an underlying continuous concept, and we have an outcome that responds to that underlying continuous concept, or at least there's no controversy about that. We just measured the underlying continuous concept really badly when we give people limited choices, but we measure it even worse when we give people more choices. Like, if you want to actually measure urban density, on a continuous fashion, you got to go to the real census data, not like ask people like whatever. Because some people might say they live in suburbia, but like it's actually closer to urban or something like that. Anyway, this is self-reported. Got all kinds of things with it, but it is probably in the right order among these three. So interval censoring. Log likelihood with entering censoring. So all we observe is income ranges. So assuming those to be conditionally independent, the likelihood would be the product of all those things. Consequently, the log likelihood is the sum of the logarithm of the probability of someone's true income in dollars falling between the wife and the wife minus one observed cut point, which in this case we assume to be 10,000, 30,000, 60,000, 100,000, 200,000, etc. And the probability of a continuous random variable being between here and there is the difference in the CDF at the top and at the bottom. Conditional on eta, which depends on beta and gamma and sigma and whatnot. So yeah, implicitly assuming that the extreme cut points, C0 and C capital J, are 0 and infinity, respectively. But the probability of being less than or equal to infinity is 1. So it works out for the last category and the first category. So when BRMS or whatever, which you can do interval censoring models, BRMS, does the log likelihood, that's what they use. Okay. Everybody comfortable with interval censoring with observed cut points? What, and this is much more common in social science, what if you have some outcome, how much do you approve of the job that Joe Biden is doing as president? Strongly disagree, disagree, and agree, strongly agree. So-called Likert scale. Measurement of the outcome. Extraordinarily common throughout the social science, particularly sociology, of which I think Likert was the sociologist. In which case, our model for the data generating process is we observe one person checks the lowest or the box farthest left. If their Y star is less than the first zeta. And pretty much the rest of it is the same as what we saw before, except now zeta is an unknown random variable that we might have prior beliefs over as to where the cut point between like strongly agree and agree is. And so we're going to need posterior draws of the zeta along with everything else. We'll know that in a second. Y star. Because the zetas are all unobserved, the Y star now doesn't have any absolute units to it. And consequently, we need to assume the errors are standard normal, standard logistic, whatever, rather than estimating the sigma, the scale of the errors. Because I could go through and multiply the Y stars by any positive constant. If I multiply the zetas by the same constant, I would get the same observed outcome categories. And so what we do in that situation is we restrict the error standard deviation to be 1, and that precludes you from multiplying everything by some constant, because if you multiply everything by some constant, then the standard deviation would no longer be 1 for the error. So the other difference between this model and the model that we were talking about before, sigma is not a parameter, and so we don't have a prior over it. Also, the way I've got it formulated here, there is no intercept. Because I could add a constant to all the y stars, if I add that same constant to the zetas, again, I would get the same observed outcomes. So in this case, I restrict the intercept to be 0, estimate a full vector of cut points. Some other software, I think Stata, so this is popular, estimates one fewer cut points, but estimates an intercept. But all you're really doing is like shifting this whole thing left and right. And then we have, say, normal priors on coefficients. Okay, so does anybody have any questions about the difference between this model for an outcome like how much do you approve of the job Joe Biden is doing as president? Strongly agree, disagree, strongly disagree, versus the model that we had before. What is your income range? Less than 10,000, between 10,000 and 30,000, between 30,000 and 60,000, between 60,000 and 100,000, between 100,000 and 200,000, or greater than 200,000. Anybody have any questions regarding the similarities or differences between this model, where the cut points are known because they're part of the answers, versus something like this, where just the answers are just strongly agree, and disagree, strongly disagree, without having like numbers. Yes?
This is a question that's not very related to that comparison, but so for the first one where we had normal predictor, we had to assume the zeta is wrong or simplex. And here it seems like you don't need to do that just because you can rescale them. Okay.
Yeah, and this is, we'll get into this a little bit. RCNR does the prior on the cut points a little bit differently than what BRMS does. And so, yeah, you can have different choices there. What RCNR does is say there's a Dirichlet prior on the probability of someone with average predictors being in the, let's say, 5 categories. And so if you think, most people are going to be toward the middle, you could do Dirichlet that's like, 0.1, 0.3, 0.3, 0.3. That would be not quite in the middle, that would be a little bit shifted to the right. That was not enough categories. 0.1, 0.2 3 times, and then 0.3, something like that. So you could have Dirichlet probability on the probability of being within each of those buckets for a person with average predictors. That's what the default prior in RCNR is. And by default, the prior on the Dirichlet is shape of 1, 1, 1, 1, 1. So all all simplexes for the cut points have the same probability a priori. And then it does an inverse CDF transformation of the thing that you put the prior on to get the zetas, which are the cut points, and then it goes forward evaluating relative to zetas. As we shall see, BRMS does something a little bit different, and let's talk about that. So your beta is the same. Let's say it draws 4 cut points from normal distributions. And let's say capital J is 5. So there's 5 possible answer categories. We need 4 cut points in order to carve out 5 answer buckets. Then we go row-wise, and so by construction over here, the zeta should be in increasing order. And the way we've drawn them here, that's not the case. But before we do anything with the zetas, we'll put a sort on it. Which actually, like, if everything's normal, the sort doesn't change the posterior period. Or it does by a constant, but that doesn't change any of the draws. Okay, epsilon, normal, 0, 1, let's say, if this is an ordinal probit model, it could be ordinal logit. It's actually a little bit more common, but whatever. Eta, in this case, we have no intercept, so it's just beta times x, although there could be more x's and more betas. Y star, eta plus epsilon, and then we cut relative to the realization of the breakpoints to obtain this ordered number between 1 and j, ordered factor with integer labels between 1 and j. As opposed to like bowling, where we had numbers between 0 and 10, but they were actually counts, not labels of number of pins fall down, count. So down. Here, just have the labels. Okay. So, main difference here. Here we're estimating the cut points, not estimating the sigma, as compared to what we had before, when the cut points were known, and that allowed us to estimate sigma. All right. So in terms of the priors, there's a data set that comes with BRMS having something to do with the effectiveness of inhalers for people with asthma. And like a new type of inhaler or something came out and they wanted to know what was the treatment effect of that new technology or whatever, as judged by the ratings that the people with asthma gave to their brand of inhaler or whatever. So we want to look at the priors using family cumulative. That's the BRMS phrase for ordinal model. Then we look, okay, as usual, intercept or the coefficients have these improper priors by default, not good. Particularly in an ordinal model because there's no sigma. Or this, it's assumed to be standard normal errors, standard logistic errors, whatever. You know, it can't be too far away from zero. So the idea that like your coefficient on something like whatever would be 1,000 is just preposterous if the errors are like standard normal. So yeah, we got to keep eta pretty well near zero in order for it to be like comparable in magnitude to the epsilons, which are standard normal here. Overly heavy tail prior on the intercept, but what BRMS refers to as intercepts is what we've been calling cut points, or what was said on the previous thing to be zeta. And that is, in my view, a regrettable choice, because these zetas don't really act like intercepts do in like a linear model, or what we did on the homework with, you know, wages or whatever. But they're labeled in the prior and in the output or whatever as intercepts. And you know, by default they have this improper prior on them, which is also not good. So anyway, we've got to put some genuine priors on those things. If our errors are standard normal, our coefficients should be reasonably close to zero on all these things. You know, we can't really have a treatment effect of 5 if the errors are standard normal to be like 5 times the scale of the error. It's not something that's likely to happen in any randomized control trial, which I guess is not good. So we do that, get the posterior distribution, and we see the summary of the posterior draws, including intercept 1, 2, and 3, which we would have called zeta 1, 2, and 3. I guess there's 4 categories of rating in this situation. We get a posterior mean on the treatment variable that's highly negative. I guess, I don't know, but I guess lower ratings were better as opposed to like Uber style where it's 5 stars or whatever. Anyway, so one way or another it seems as if there's some sort of a treatment effect, even after adjusting for like what period the study was in and some like dummy variable for how often do you actually carry it. I guess I don't really have asthma, but I suppose they don't the bottom, again, don't get confused by this. Family-specific parameters on the dispersion. This is fixed to be 1, which is to say the assumption of the bottom errors are standard normal. Could have been standard logistic, but either way, the scale would have been fixed to 1 to avoid the multiplicative indeterminacy. I can multiply all the y stars by a constant, multiply all the zetas by a constant. I would have observed exactly the same thing out of the model. But also this business of not estimating an intercept the way Marcy and Arm thinks about it, or only estimating one fewer of the copoints the way BRMS thinks about it, is to preclude the additive indeterminacy. And I can add a constant to all the y stars, add a constant to all the zetas. And what I would observe is exactly the same thing. And so usually we want to eliminate those indeterminacies from the log likelihood functions. Frequentists have to, in order to get maximum likelihood estimates. Bayesian, strictly speaking, don't necessarily have to. Like, stuff is identified for any proper prior, but it tends to work better computationally. It's also more similar to frequentist results if you make the same assumptions, and also so kind of the underlying lesson of these y star variables, particularly if none of them, the y star is observed, I guess for the homework, most of them were, but a few of them aren't. With these y star things, they're not meant to be interpreted cardinally, or really even numerically. They only matter relative to each other, or relative to copoints. Or like the thing we did last time, with the unordered categories of orange juice, which gives you the most utility. That's the one you're going to buy. So utility is not like a concept where we can really put ratio scale numbers to it. But if you say, okay, I get more utility from Tropicana than I get from any other brand of orange juice, then it's reasonable to predict you're going to buy the Tropicana as opposed to something else. And that raises a question that I meant to address on a discussion, because Keith mentioned it to me from the recitation session, is that in the example that we did with the recitation, it was about voting in an election. And we had some different types of predictors that we did when we did this in class with the types of the species of iris. So what we did last week with the species of iris, we only had plant level variables in that maze. The petal width, the petal length, the sepal length, the sepal width, that's it. So everything we observed was plant level or observational level. And that made it kind of simple. But for a lot of things in social science, you might have different types of variables. And so the way in which a lot of these unordered things are used in economics with orange juice or whatever. So predicting how much of what kind of orange juice would people buy. Well, the starting point for any microeconomic thing is what's the income of the consumer. That's a person level characteristic. And so my income is whatever it is, irrespective of what orange juices I'm offered at the grocery store. But the second thing, what's the price of the different brands of orange juice? And those differ, but the price on the sticker is being offered to everyone who comes in the grocery store, irrespective of their income. So price is an orange juice level to predict. And in the case of the elections thing that we did in the recitation, we had some of both. We had person level things like how religious are you, urban, rural, whatever. But we also had this variable which is really kind of an interaction between the party and the person, which is based on your ideological distance between the person and the party that the election was between. And so we had these ideological distance things. And in the recitation, we made an assumption that, or we wanted to make an assumption. BRMS didn't actually allow us to totally do it when we drew the book here, but we tried to make the assumption that that coefficient was the same for all the distance variables, but like when it went into the ADA or whatever, when evaluating your utility for the Labor Party, we only used the labor distance and the person's religion and urban thing. We didn't use the distance for any of the other parties to predict whether you would vote for Labor. But the other four parties, we used the respective distance for them, whatever. So different sorts of variables, we can make different kinds of assumptions, but the kind of genesis of that sort of a model used in these models for multi-party elections is you vote for the candidate or the party that is giving you the most utility. And so it's always, relative to the utility you get for any of the other choices that you can make. And so when none of these Y stars are observed, they're not really in absolute units. They're only in relative units, which is why we have sometimes, or always really, multiplicative and or additive indeterminacies that we need to flush out of the likelihood by fixing the errors or the intercept or whatever it may be. So anyway, this is how we draw. That's the priors we don't use. If we use those priors, which are much more reasonable, this is the posterior distribution that we get back. But when you look at this thing, you say negative 0.046 is the posterior mean estimate of the treatment effect. But that's in units of eta, and the units of eta are not absolute. So what can we do with this? Well, we can do a lot of things that are bad, and we can do at least one, but perhaps at most one thing that is good, which is to use the conditional effects function in the BRMS package to visualize the probability of someone giving rating 1, 2, 3, or 4 to their brand of inhaler as a function of whether they were in the control group or the treatment group. And when you have multiple levels, different things can happen when you're in treatment relative to control for each of them. And so, as we can see, for people in the treatment group, they have a much higher probability of giving rating 1 to their inhaler. But because the probability is sum up to 1, the probability of something has to go way down. And in that case, the probability of giving rating 2, much less. So the treatment effect on the first category was positive. Treatment effect on the second category was negative, which is to say whatever the intervention was, tended to make people who otherwise would have given it 2 wrong. It didn't really have much effect at all on the 3 and the 4. But that's kind of what you need to think about when you have these ordinal things and hence probabilities there. Okay, out of time. Recitation, office hours on Tuesday, no new homework, start to get into multi-level